Hi everyone, welcome to the homework solution walkthrough video. Let's work on the example 2.1. In example 2.1, we are going to simulate this circuit with these parameters. Let me show you quickly about the MATLAB Simulink model. This is what we make for this example. So here you can see we built this model here. This is IGBT, and this is the switching signal, and this is the impedance resistance, and this is the voltage, which is this one Vs, and we have the BDC over 2 DC source here and here. Here you can see that we are changing or specify the value for the DC voltage by using the controllable voltage source. And here you can see we enter the DC value here, and let's see the specify the Vs and BDC over 2. So here I can specify how much is the DC voltage or half of VDC voltage. And here I can specify the Vs voltage. One thing to notice is that in the simulation, I made the variable name here, the Fs, which is a frequency, switching frequency, and also the parameters of this resistance and impedance. And I make it a variable name. In order to get that value, you need to run this init.m file. And once you run this file, and you can see all the parameters will be defined with this number. And once this is in the workspace, you can go back here and compile, going to the modeling and update the model. And here you can see that this parameter will be updated with the specified value. So here you can see the R is 0.005, which is coming from here. R is equal to 0.005. So this is usually what we enter the parameter for the simulation. Of course, you can enter the parameter directly inside the dialog, but if you want to change it, you need to go to this specific block, which may be time consuming, especially if you have many, many models. All right, so we can run this simulation uh, here. Let's run it very quick. And just want to show you here, let's run the simulation. Yeah, here it's different from the homework. In the homework, the transition time is at 0.2, 0.7, and 1.5. And in our simulation, yeah, we need to wait until you reach a steady state. Until after we reach a steady state, we apply the disturbance. So this is why in our simulation, I make it to be changing the modulation index at 6 seconds because it may take some time to reach a steady state, and then I will change the modulation index. All right. And similarly, I change the Vs value at t equal to 12 and change the VDC over 2 voltage at t equal to 17. And this is why I simulate the whole simulation at 25 seconds. So let's run the simulation very quick. It takes some time, but yeah, it's not that bad. Okay, so once you run the simulation, you can go to the simulation tab and you can go to the data inspector. Okay, once it's finished, you can click on data inspector. All right, and in the data inspector, you need to sorry, this is my previous simulation. Different layout. So you can go to the open set view and you can select I provided the example 2.1 view updated here. So this is the, uh, you can see a pre-saved layout for the waveform. So you can easily see that for this is the current, this is the power, real power at this terminal. the PT, and PS is the one I calculate here. And here you can see for IP and IN waveform. And here you can see that we changed the modulation index as 6 seconds. So that's why the current is increased. And then we increase the VS. And since we increase the VS, uh, the current will decrease because here you can see we have a higher VS. The current will drop. And then we increase the VDC over 2 at 17 seconds. And then since with the fixed M and fixed VS, the current will increase. So here you can see is the um, you can see the trend of the I. And correspondingly, you can find the PT and PT filter. If you see the PT here is have less oscillation, which makes sense because if you check the I let me show you the IN current. No, the I current. I see here the current here, which is I. Let's see what does I look like. The I will be look like. Let's see. So you can see the I also have the oscillation because it's switching. Okay. But if you do the average, you will be like the DC current and just like the filtered DC current. Here you can see like this one. Okay. And if you do so here you can see in my calculation, the measurement, I do the IN and IP, the current coming through these positive DC source and negative DC source is IP and IN. And both of them is fluctuating. And I do the filter, low pass filter, and you can see one is orange is IP filter and the brown one is IN filter. Okay, so here you can see the difference. And the PS, how do I calculate the power at the load, which is here? Basically, is the voltage Vs measurement times I, and I do the filter, do the low pass filter. So here you can see the PS is the current times Vs measurement. So this is the instantaneous power, and I do the low pass filter to get a filtered value. Similarly for PT, the power coming at this location, or you can see the power coming into here. And this is the current I times the VT measurement. And of course, I do the low pass filter to get the average value. Interestingly, if you calculate the PDC filter, meaning the PDC coming into the IGBT, or to be more precise, the PDC coming here, is two components. One is IP times this VDC over 2, and also IN times VDC over 2. But notice that this VDC is reversed. So this is why I need to plus the PDC positive part and minus the PDC negative part. And you will see that this will match the power balance. So here you can see, let's see here. Here the PDC positive is 6.65 and negative is 1.27. And you need to do the minus or to do the difference. And you'll get 5.737, and which is very similar to 5.04 and BT is 5.36. And you can see that the PDC 5.37 e to the plus 5 is a little bit higher than 5.36 because we have some losses in the IGBT and we have even lower power to the VS because we do have the resistance. resistance power. So the power, the PDC is greater than PT and is greater than PS. And here you can see the relationship between PDC filter, PT filter, and PS. All right. And of course, we can play with different variable. If you increase the inductor L, and you will see that the ripple will be reduced. Let's do the very quick. Let's see. Let me pull out the filter here, the I. So here we can see I here, right? And then let's do the quick screenshot here. So this is, and the L is the original value. Let's put here just for comparison. And let's increase the L by 10 times. So let's say 10 times L, and then we run this M file. So L is is increased by 10 times. And then we can run the simulation again and to see what happens. Okay, hopefully, yeah, it's running. And right now you can easily see that the current ripple, the purple one, is much less compared to the previous one. Okay, let's make it run. But in the steady state, the steady state value remains constant. All right. So here you can compare this with that. And here you can easily see that this is the smaller inductor and this is larger inductor. Here you can see that the larger inductor, the smaller the current ripple. All right. Okay, so this is something I want to show you in this example. Yeah, basically the the power and the current in different location. Okay. One thing I would like to mention is another thing is the simulation time step. Uh, of course, it's easier or it's better to have a smaller time step. So this is okay, but if you change this to a larger number, let's say change to 4, which is the 100 times bigger, the simulation will be much faster, and but the simulation result will be very not accurate. So here you can see the simulation is totally different from the previous case. So you need to make sure your current the time step is small enough. All right, so let's change it back to 6. And here you can see the current will go back to normal value. All right. So it's important that you need to find the right time step. Typically, the smaller, the better, but you need to know that the smaller time step, it will take longer time to do the simulation. All right. So this is something I want to talk about for this example, the example 2.1. Okay.